Yes. So good evening, everyone. Nice to meet you today. And particularly like this week or in the previous week, what we did was start with PyTorch basics and we moved into convolutional neural networks. And in the last session, you saw how you could make use of like local data sets or custom data sets. That's data sets that has not been maybe pre-processed already. So in which your own kind of data sets and how you could work with those particular data sets. And we briefly went into the topic of going modular. So how you could maybe arrange your Python or PyTorch code in a very well-fashioned way so that it will be easier for you to make a very good workflow in which that would kind of accelerate your, let's say, deep learning processes. So, and particularly like this week, we will be doing something entirely, not so much different, but something relatively new. And it's new in the sense that it's maybe still one of the state-of-the-art methods, but still focused on computer vision its own self. So what we'll be doing today is primarily transfer learning. And yes, so I will just go into it just briefly now. Yes. So still, like this is the main resource. The main resource is by Daniel, and this is like our own GitHub page. So I've just done some bit of updates. So you'll see like there is some updates with the timeline, but I'll talk more on this maybe towards the end. So the primary focus is on this particular resource here. So PyTorch transfer learning here. So, and yes. So let me just select like a compute to use. So we'll be using like this notebook for teaching this course. So here we will just talk about high level, what transfer learning is, and also maybe briefly touch into some of the models that you could use for transfer learning. And yes, so primarily when you talk about transfer learning, it's more of like you have a particular model that works really well in a particular instance. So how can you transfer what that model has learned into a different setting? So that different setting is like what you want to work on. So that might be a problem you are focused on itself. So to put it simply in a way, imagine you have some kind of new task. You have some new tasks. Yes. And that new task, it's maybe you could just say it's, let's see, tailoring in this particular case. And so the task is in on, okay, just 1 minute. So let's say tailoring in this particular case. So how you would want to look at it, there are maybe two people that you are looking to choose one out of those two people to execute that task for you. You have, let's say, someone who is maybe less than 2 years, and you have someone that is maybe, let's say, 21 years old, but has some kind of engineering background in some particular case. So you could see like both of them they don't align with your task, or they can't really perform the task exactly as it is. But when you look at it, like this particular person here, he has like some capacity to learn, but it is majorly empty. And this particular person also has maybe, let's say, relatively the same capacity, but it's filled with another different task entirely. It could like it would perform a different task. So, but when looking at it, it's much more easier for the person who has some engineering background to work on like some tailoring kind of tasks. Why is that? When you look at it, like the person having engineering, maybe in terms of thinking, he has already grown his thinking, and it's easier for him to just switch from engineering to tailoring because he has like some idea of how like locomotion, how maybe engines work. So it's easy to just step on his tailoring machine and maybe operate it in one particular instance. Another thing you could also look at is like the time it takes to learn tailoring. for someone that is maybe 2 years old, it will take a relatively long time because like one, there is maybe the age progression and you look at the investment you would make for that person to learn. So, but someone that is in engineering, so I'm just saying, for an example, so it takes relatively less time and less resources to train that person to learn how to do tailoring. So that's like the idea of transfer learning. You take something that works well in a particular domain and apply it to another different task. So that's like the entire gist of transfer learning. So you build this model that works really, or someone else build a model that works really well on one particular task. So how can you like change or adapt that particular model to work on a different task? So that's transfer learning in its own. So, and usually like when you look at machine learning problems or deep learning problems, what they aim to do, they just aim to do like one particular task. So when you look at the GitHub page of maybe a machine learning project or anyone, you would see maybe deep learning classification for maybe a particular medical disease or something like that, or deep learning classification for crop detection between maize or maybe some other plants. So they do a particular task. But in this transfer learning, you take a model that works, like we said, on one different task and adapt what it has learned to another different task. So in the next part of the notebook, I'll just go through the codes while explaining some main parts of transfer learning for you. Yeah. So I'll just run through the notebooks, but if you have any questions, please feel free to just either on the chat or you could unmute your mic and just speak, no worries. And if you also want to contribute, feel free, please. So, and please, if we could all unmute our mic, if we don't have anything, just don't, so that we don't distract each other. So I will just keep running the cells. So if I find something and explain maybe anything along the way for you, but if there's anything I miss or you don't understand, and I will be glad to maybe recap or explain further, inshallah. So in this particular setting, what they did, it's like use the previous like data or steps that we used. So we won't cover that. So we just go into like what we want to discuss mainly. Inshallah. So can we kindly please mute our mics? So there are, like with deep learning models, which you have trained some in the past. So one of which you've trained is like just a basic CNN. And I think previously you trained another different, much deeper architecture. So there are different places where you could see those networks. So one of the main places you could see like different models that are designed or built by people is like mostly are like from papers. So most of the common architectures are from research papers that are built by people. And it is often replicated by one or two frameworks. So PyTorch has this, when you look at its own like torch.vision here model, so it has like some architectures there in which you could just import easily and start to use as soon as possible. So Hugging Face is one popular like repository for machine learning or deep learning models and even large language models. So you could like look at it and kind of fetch one or two models from the Hugging Face hub in which you want to use. Then Team, even though not so popular, but it houses like, yeah, it's still popular. It houses like some really good, it's mostly focused on computer vision models. So it houses like a very large number of like computer vision models in which you could use. So I believe like there's some kind of collaboration between Team and Hugging Face. So it's also worth looking at. Then there's Papers with Code, which would be nice to look at. So with Papers with Code, what you have here, you have collections of papers and their existing implementations. So why I like Papers with Code is like you could look at a particular data set and look at like what architectures have been used for those data sets, or you have like some kind of benchmark in which you have the performance of different models in Papers with Code. So they're all like different locations in which you could look at, and particularly in your next capstone project, you make use of this. So it would be very good to look at this and look at the models they offer you to see how best to go about it. So just moving further. So all this, I think we have done them in like the previous session. So one thing that is new is this touch info here. So with touch info here, it's like a very simple but very important library. So it has very huge benefits. So it helps you kind of have some kind of visualization of your architecture. So if you have used like TensorFlow before, so you know in TensorFlow, you could just do model.summary. You could just do model.summary. So, but in PyTorch by default, you don't have this. So that's where like this touch info comes in. So it helps you like perform, kind of look at some textual information of your model. So it helps you in that very much. So we'll also look at that. So you will see like an example of how that works. So in this particular case, we'll just do some importations and just get started with the important parts of this notebook. So this might take some time, but I'll just skip it and just go to what's important. So like I said, we'll still keep using like the data from like the previous notebooks or previous week's session we talked about. Yes. 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 So yeah. So I think this will be like the very first beginning where we'll talk about how we could apply like what's the name? Some model someone has used before to train our own to perform our own tasks. So when you look at it, you remember in our discussion where you have like a neural network. So one of the two important consideration of a neural network is like the input and the output. So they kind of govern what your model will do. So for instance, you could look at, let's say you are considering a simple neural network in this particular case that has some kind of hidden layer and you have some kind of output layer here. So this is your input layer and this is your, let's say, output layer here. So what governs the input is like the data that is coming in. So depending on the size of the data you have coming in, so that's what determines what's the kind of architecture or size of your input layer. And the output is defined by, let's say, your labels that you want your model to predict. So similarly, let's say you are trying to work with a different data set from someone else that you are using. So assuming, let's say Muhammad has built a very remarkable deep learning model and you want to utilize that particular model for a particular task. So there are also things you should take into consideration. So let's say our assumption is his model has some kind of input, yeah? So, and before passing to his input, he has some kind of before passing to his input, he has done some kind of operations on those like tensors. Yeah. So these operations can be maybe a number of kind of operations, or we could just simply say transforms. Remember the transforms in which we covered in the last section, something similar to that. So when you want to use that model, it also makes sense for you to perform those kind of transformations before passing your input into his own Muhammad's model. So that's where like this idea comes in. You have to understand what's the transformation made by someone in someone's model and how you could apply that into your own model in that particular case. So here, I think the major part of this point is to kind of look at some transformations that has been used by a model called EfficientNet. So don't too much worry about the detail. I think the major thing is to understand it works. But I think later on, I'll just give you some high level idea of how this one or two models are important or one of the key ideas that makes them important. So in making or in adding those transformation. So you remember, like, we have a number of transformation, one of which is like resizing here. So if you remember, like, compose here, just to like kind of combine all your transforms together, then you have resize. So one thing is key, like we said, like your input here must always align with the input of the model. That's your data input and your model input. They must be in the same shape if you want like the operations to go in the same manner. So one thing you need to do is make sure like the input size is the same as what the model is expecting. If not, you need to resize it. So that's why resizing is done in this particular point. Then here is just more of like converting the input from the data and converting it to tensor. In most cases, like most of the data are in maybe NumPy array, or it could be like a pill kind of object. So you want to you want to convert those objects into like touch tensor objects. And finally, you'd want to normalize. So just to recap back to like resizing. So just recap back to resizing. So when you look at it, let's say you have this model that works, and by default, it uses, let's say 256, 256. So what happens is when an input comes into this model, it performs some kind of transformation, reducing the size almost at each layer. So, and let's say towards the end, you have some kind of output. Let's assume our output here is 10. And here, your 256 might be reduced to, let's say, 214 or something of that nature. But in the case where your input is not the same size as this, if it's bigger, so it's totally fine. But if it's smaller, let's say you pass in an input of maybe 54, it causes a problem. So where it causes a problem is where your convolution or your convolution kernels needs to work on an image that has 54 by 54. So it raises an error because it starts by reducing the size, and after some points, your convolutions will not be able to work on that particular size. So it's always mindful. Look at what the input of the model you are using, what it's using, then try to resize your inputs to use that particular input, or maybe something larger if possible. That's one. Then another thing you might need to do here, it's called normalization of your data. So when you look at it, because like you are dealing with images of, so all your images are different, they are not the same images. So it's likely they are taken, those images are taken where you have like light of different intensities. So, and what you don't want to happen is like image of one affecting the other. That's in terms of maybe intensity or any variations that could happen within images. So what you do usually is normalize using like the mean and standard deviation. So what happens in this case, like all the images are within a particular range. So when you train this within this particular range, so it's much more easier for your model to learn when you have standardized the images. So that is why it's very important to normalize the image. So you normalize using like some metrics. That is, so in most cases, like this normalization, these values here are what is from, these values here are what is from like the model you want to use. Let's say this, the architecture of this model. So these values here are what has been used to like initially train this model. So that is what you would use to also normalize your own data. So after having these transforms here, so what you do, you pass the transforms to your data sets. You remember how you have the workflow for PyTorch, where you start moving from data set, data loader before training. So I think there's a question from Bala. Yes.
Yeah, my question is that what happens if somebody changes the means and the standard deviation?
Yeah, so I think nothing serious kind of happens in some way. So the only issue you might have is it might take a longer time for a model to learn. So if you remember, like when you, let's say you change the mean and the standard deviation. So you remember like you have, let's say you have, let's say this is your model. and it is, and you have like some data coming in. So when you change like some kind of value, maybe within the model, so here has like some parameters. So it will try to adapt those parameters based on like some values you set here. So even when you set another different mean, your model will find a way to account for like those particular any change you have. So like your model is just like a mapping from like your data to your label. So any transformation you have, so it doesn't really matter any change you make to your data, it will just try to find a way to fix it to kind of fit it to your labels, just to make sure like the predictions are accurate. So when you change the mean, so it's very likely it takes a longer time for it to learn based on like the new means or any deviations that you have. Thank you. So yes. So I think that's for transforms. So, and here the batch size is set to batch size 32. So like batch size is a hyperparameter, you could set it to anything you want. And maybe you could monitor how it changes with time, just so that you can make the proper, so that you could like get the best results. So you could start from a smaller batch size and increase as much as possible. So yes. So here, so what they did here is more of like you have some. So like from going modular, you compose your. Please, can we kindly mute? You compose like your existing kind of code for training and testing like your data set. So what they do is like from this, like you have some kind of methods and modules. So you can just call those modules. So here you just pass in the directory for training and directory for test, then the transformation you have in this particular transformations, and maybe the batch size. So it does like it loads the data sets for you. So it performs like definition of your data sets and your data loader. So what it does, it returns like a train loader and test loader in which you could directly use to train your model. So, and what you could see here you could understand like we manually set this out. So, but in the newest kind of iteration of touch vision models, so it comes with, you don't need to manually set this out. So it automatically comes with like the transformation that has been used by default by the model, and you could just pass in your data and perform the transformations by default. And it has like some pros and cons. So in most cases, like you might not want to use this transformation, or you might want to add additional transformations, maybe some rotations or some kind of specialized transformation that you want. So since it comes automatically, so it might be, it won't be easier for you to change. But with this kind of manual transformation, so you could set the transformation like the way you want it. And it was a nice question by Bala, because if you perhaps find better values or better means that better aligns with like the task at hand, so why not use that? So which will be very good. And yes, so we talked about like in transfer line, what you majorly do is like use an existing train model and try to fit it into your data sets. So how would you load this existing train model, which you could see easily you would like import from PyTorch models. So with PyTorch models, what they do is like they already have like some established implementation of those models that are really good. And just to give you an example, like AlexNet. So AlexNet won the ImageNet competition sometime between 2012. So instead of you maybe trying to reinvent the wheel already, so they kind of have written some standardized code for you, which is stored in Touch Vision here. So all you need to do is just import and you get started as soon as possible and try to train. So there are two components of this. So one important part is the weight. So if you remember, like in the last lecture, we talked about like in your machine learning kind of pipeline, everything is like a sequence or a set of numbers entirely. So what they do here particularly is to store the weights, which is like a set of numbers. So those numbers are kind of those parameters that has been learned by the model trying to fit like on the ImageNet tax. So the ImageNet has like, it's a kind of competition that has about 40 million images and about 22 or 220 classes. So these weights here are parameters that have been learned by the model, and they have been able to like really work really well. So what you want to do is like load this weights and just get started with the model as soon as possible. So yes. So here, what you could see here is, here we are just kind of importing the weight from Torch Vision and EfficientNet, and you have some weight. So default here means it's something like the best weight available for this model. So EfficientNet is like a kind of architecture that has been like developed by someone based on like some research, and you could easily call like any model you have. So there are other like networks like ResNet and let's say VGG. So easily, when you want to find other kind of pre-trained models that exist, you could either look at the documentation here for Torch Vision, or easily, if you maybe are feeling lazy to maybe open a new tab, you could just maybe something like this. So when you run this, you see, so with there here, it's a kind of PyTorch maybe default function. So what it does, it returns you properties or methods that exist under this maybe Torch models or any PyTorch, any Python object. So here you could see there is AlexNet and there's the corresponding weights. So you see there's ConvNext, which is also a very good network, and you see DenseNet of various like of different variations. So where you see like weights appended to it, this means like basically means the numbers of those like numbers or the parameters that have been learned by the model. So, but where there are no weights, it's just like the object itself. So think about this as, let's see, this is just a container itself, and this is like the numbers that you need to insert into that container. So that's majorly, I think in the next cells, you see how this works better. So as you can see, like in the weights here, it has like the default transformations, which is here, which is good. So you could see like these transformations here are like what you initially set for your model. So here it has like a resize of 256. So why is this 256? The model by default accepts like an input of 256. So when you have an input, so it tries to transform that input. Actually, 1 minute. So here, what you could see here is in this initial spot, you have like a cropping. So imagine you have an image, it could be by any size, maybe 520 by 520. So here, a crop size does a kind of cropping, and it returns an image of 24 by 24, 224 here. So you could resize it to another larger image of 256 by 256. So this resizing, there are various methods of doing the resizing. So one is like called interpolation by cubic. So there are various other methods you could use for like resizing images. So yeah. So I think that's majorly it for here. So like we said, like transforms, like the new PyTorch Vision models comes with like the transforms by default. You don't need to set it manually, which is good, and it helps you to get started as soon as possible. So you don't need to bother about the numbers for normalization. So here, this is like the default loading. So like we said, like pre-trained model is a model that's been used by someone else, and being used by someone else and you want to use it means like it has learned to perform the task effectively really well. So since it has learned to perform the task really well, you want to utilize it for your own particular task. So one thing you would notice that all of them are kind of deep learning models. So they are deep because like they are really like a cascade of very deep like convolutions and fully connected layers, which learn to perform the task effectively. So one thing you could notice, like everything here is like as a result of research. So what you would notice, like since the first kind of CNN. So you make an improvement on it. So it's like a series of improvement. Everyone comes, researches, and makes some improvement, either made by accident or knowingly by theoretical experiments. So one thing you should note that in each of these architectures, each of them has like some kind of key ideas that make them stand out really well. So what you would notice, let's say, just taking this, for instance, ResNet. So the idea is, let's say you have, so assuming I take everything to be maybe just rectangular in this particular case, let's say some series of networks, assuming your input comes here. So what happens in the very long run, and you want to train it to have like some kind of output here. So what happens here, you remember like back propagation, your data goes forward and you do some kind of back propagation to learn it from your errors here. So what happens when your network is really deep? So you have what you call like kind of vanishing gradients. So where you have like gradients, let's say, assuming, let me just say the theta here. So at some point here, where you want these gradients to go back into this network, at some point the gradient becomes 0 here. And there is like visibly no change in your network. That's the initial layers. So this, in the initial idea for ResNet, is why not we have some skip connections. So skip connections basically means instead of having just connections that is forward, so why not some connections from the initial layer just skip to maybe some layers at the very front. So that was their key idea in ResNet. So you could also look at the paper and see if there are any other information, but this was the kind of key idea or highlight for ResNet. So, but we won't really go much deep into it. Let me just see, seems there is some question. So there's a question from Abdurrahman, the mean and standard deviation above, is it your own data or is it from the adapted model? So like the mean and standard deviation, at first, what you try to do is to use your data, that if like the model, it's your own. So the mean and data is from the original data that was used to train your pre-trained model. So in this particular case, in the case of like EfficientNet or ResNet, so ResNet was originally used to train ImageNet. So the mean and standard deviations from like the ImageNet. So thank you, Lukman. Yes. So the mean and standard deviations from ImageNet. So what you do is use those standard deviations from ImageNet and use to train your data. But let's say you are not trying to use a pre-trained data, you are trying to use your data. So the mean and standard deviation would be from your own data sets. So what you do, like you take all your data set as a whole, then try to calculate the mean from your own data sets. But since here you are using a pre-trained data, you use the mean and standard deviation from ImageNet itself. Thank you. And yes. So I think next, so like I said, like each of these models has some kind of key idea in which they use. So in VGG network here, so here, one of the challenges too, so VGG was much more earlier than ResNet. So in VGG, they said, why not? Because like before VGG, there is, I think people usually use very large convolutions, maybe 5x5 convolution or 7x7 in AlexNet. So VGG said we can actually go deeper, but still using like some 3x3 kind of convolution. So when you have this 3x3 window, it could kind of give us the opportunity to learn better and even go deeper, where you have like smaller convolution, but still going deeper and learning. So that's like the key idea. So each of these papers, they all have their key ideas. So it's usually good. Let's say you want to use a pre-trained model, try to understand what's the key idea, just so that you could also make some modifications. Because when you take a pre-trained model, you definitely will need to make some modifications after let's see, after loading the pre-trained weights. So yes, so I think I'll just go forward a bit. Please, if you have any questions, feel free to ask. So I think like we said here, when you have like a higher number here, signifies better performance. So it's something to do with some kind of versioning. So, and you would also see here, some, let's see. Okay. So you also see here, like, remember, like when we try to just see like what models are. So you could also see here, like, let's say you take VGG, for instance, you could see VGG 11, VGG 13, VGG 16. So these numbers here relates to like the depth of your VGG. So, like the deeper you go, like theoretically, like the answers should be like the better a model is, but that's not always the case. So sometimes you need to have some trade-offs. So one other kind of variation you have some kind of BN, which is batch normalization. It also helps in training. So yeah. So I think the next thing we'll just look at is how you could load those weights. So like we said, like the weights are just numbers. So how can you utilize those weights that you have? So here, what you do is you basically get the weights from touch vision models, then call the model you want to train. So here we are calling efficient nets to get the weights. So by default, we want to get like the best weights available. If some kind of situation you want to get some other kind of weight, so you could also do that for your own training. So here, what you do is like to call like efficient net. We kind of simply call this like a kind of container. So when you have this in its own self, you have like an empty container, which basically means you have like an empty structure of your efficient net. But you want you to use like an already pre-trained network. So you want it to use an existing weight that has really learned to perform the task really well. So what you do is to pass this weight here into like the model container that you have here. And depending on, let's see, what device you're using, move that device to either CPU or GPU or maybe TPU in some other case. So I think that's the next step for us. So when, oh, let me see. Let me just try to run everything from the beginning and let's see. So I think for simplicity, maybe we'll just try to use another model and see if maybe something better comes up. So let's just use this for now. So yes, so for now we just use the ResNet model. So I think maybe an issue with like the efficient net model, but I think maybe it's something that maybe can be figured out. So yeah. So I think this comes to like the next important point. In the earlier part, we talked about inputs. So your inputs of the model must align with like what's like predefined for a model. So one other thing you could look at is like the output of your model. Because when you look at it, like your pre-trained model that has been trained by someone else, the output is in most cases not the same as your output you would want. So like let's say in like ImageNet, so here you have like 1,000 classes. So, but let's say you are dealing with a very simple problem, like this particular case where you have pizza, steak, and maybe something else, you have 3 classes. So you must have to find a way to reduce those 1,000 classes to 3 classes. So that in that way, you know, like your model will map from your data that uses your data sets into like 3 classes you want to predict, which is pizza, steak, and yeah, something pizza, steak, and sushi. Yes. So, and what you would notice, like in most architectures, That's like in PyTorch, by the way, but like when you use other architectures that are outside like the PyTorch model. So what you majorly need to change is here. This is the classifier. So this determines like what's like the final output. So you could define any number as it goes. So which is something you would see here. That's the output features here. So yes. Let me just clear this. So like we said, please, if there's anything you feel like maybe you don't understand, just feel free to just call my attention. So remember we talked about model info. So model info has this summary kind of method here. So with summary, you get a kind of visualization. Like when you have an input to your model, how will the input be transformed like at every layer of your model? So when you run this model summary, so you could see we are using a ResNet, and you could see like some kind of idea of like the architecture of the ResNet, which is arranged in blocks. So when you pass in like an input of this size, so here, this input is more of like, we are telling you we have an input of 224 by 224, which is of 3 channel here. And we are one batch of input, so should contain 32 images. So what happens when we pass this input into our data set? What will happen? So it does some calculations looking at the input and the architecture of the model. And you could see at, yeah, so, okay, so here, looking at the input shape here, you would see like at the very first glance, when you pass in like a set of images here, so almost nothing happens here in the first 2 convolutions. So you could kind of set a convolution that returns the same input as the output. But when it begins to go deeper, when you look closely, you could see like the size of the images starts to decrease. This is because like of the convolutions acting on it. And it's going deeper. It's going deeper means like you are having like an addition of channels. You could see by 64, and with time it keeps increasing, while like the original feature maps keeps decreasing. So at some particular point, what you do is to convert this, to flatten it out into just one very kind of long array, in which you just use the fully connected layer to just make your classification. So at this particular point, you have something kind of flattened out, and you use the fully connected layer and transform it into like to your output here in this particular case. So it also kind of gives you an idea of what are the total parameters you could use, both trainable and non-trainable. So in this particular case, you have non-trainable. But like for you to really pre-train well, you would see like you might need to freeze some particular layers of your very large model and get the advantage of pre-training. So in pre-training, okay, let me see, 1 minute. Let me just, yes. So looking at freezing, so the idea behind freezing here is where, let's say you have some very large layers. Let's say you're considering a very large neural network here that does some kind of prediction. And in the very output, you have, let's say your output layer here. So here you are expecting some kind of set of image inputs. So the idea of pre-train, or first, when you look at it, you have like initial layers and you have some kind of final layers. So when you look at the initial layers, what does the initial layer do? The initial layer learn like some low-level features, and low-level features means they are just kind of edges or patterns or textures in an image. So when you see edges are just kind of lines that happen in an image. Then you also have like something maybe like pattern. So it could be like just a dot. So this is the responsibilities of these low-level features. So one advantage you have like using pre-trained model, it has already learned these low-level features. And what you would want to do is just to utilize them as it is. So what you will do in that particular case is just take a section of your of like the pre-trained model and just freeze it. That's no training occurs here. And most training will occur on like the final layers of your neural network. So these final layers is what you define yourself. So for most people, what they do is like the final layer, which is the classification layer. So that's where like some learning happens. That's where like gradient descent happens. But in this particular part that is being frozen, so no learning happens. So there's no gradient descent. So it's like stick to where it is. So the benefit of this is like, since the model has already learned before, so when you want to adapt it to your own particular task, so there's no need to like start learning from scratch. You will waste resources. So you want to use the benefit of some already pre-trained model. So what you want to do is to adapt like the final layers to like the new tasks you want to do. And in most cases, it works like remarkably well. So yes, that's just the idea behind freezing. So in the initial layers, you learn some low-level features like edges. So how you could look at this is, let's say you have an image classification model. By image classification, so the initial layers, what they would learn is more of like edges. So just maybe it could be straight lines or like curvatures of maybe the eyes or some kind of lines, or maybe it could be patterns within the face, or patterns, let's say when you try looking at let's say terrains in particular case, let's say when you look at a grass, let's say some grass, or you look at like sandy surfaces, you could see like there is some kind of level of repetition within those particular surfaces. So those are known as patterns. So like your neural network could learn these patterns in like the initial layers, and you don't need to like repeatedly learn it by like training all the pre-trained neural network from scratch. So you just freeze up some section of neural network, which you know has some pattern recognition already in it. So, and you just learn from the final layers of the neural network. So, yes, so let's see. So this is where the freezing comes in. So what you do is you look through your model, the parameters of like the feature. So when you look at the architecture of the model, you would see, let's see. Okay, I think not yet. 1 minute. Okay, so what happens here is like you look through every like initial layer of the model, and what you do is requires grad equals force. So what you do is here, anything to do with gradient descent is turned off. So here in your entire model, there's no gradient descent happening. So when your model is doing forward propagation, forward pass, and during the backward pass, it doesn't change the parameters of the model. So if this is false, so it means like no backward propagation happening in like your entire model. So, but later on, you would try to switch the linear layer. So, but with linear layer, you add like required grad here to be true. So in that particular case, like your final layer of your model has the ability to perform gradient descent. So in that particular case, it will adapt the parameters of that final layer and to match the output of your predictions. So what you could do here is, yes. So here you could, by running the code, like we said, it looks through. Okay, I think that's my part. So here features, I believe it's part of like the efficient net, but let's see. In ResNet, you don't have features. So that's why like the naming convention is a bit different from maybe every model. So each model has the naming convention. So I think it will be very good to be careful with the naming conventions. But if you were using EfficientNet, so it uses maybe some subpart of the model is features, and you look through all those features just to freeze the parameters here so that they don't require gradient descent. So, but this is ResNet. So ResNet has like a different naming convention. So which is like conv and the rest. So it's not really packaged the same way as EfficientNet is. So that's why we have this error here. But I think I will just skip and briefly talk about the next part. So remember we said what in most cases you might need to do is to change like the classification. But this classifier here is just like some this classifier is just like a naming convention that's used by PyTorch. But when you use different other models, so you have like a different naming convention. So it's usually good to like kind of look key into the model and see how everything works. So when you want to, I kind of change the part of the classifier. So it could just be a like neural network, but it's just fully connected. So what you have usually, like you have some CNN layers at some particular points, then at another point you flatten all the inputs, then you have a kind of one-dimensional array. And you have neural networks here that do some predictions into your output. So what you want to do here in your pre-trained model is like to attach a new classifier here so that it could predict directly based on your own labels that you have, so that it will predict on that. So in the layer, so you could have like various layers of linear layers, but in this particular case we just use only one. So this here is like this number here is when you flattened out like the final layer towards your fully connected layer, which is this point here. So what's the size of this fully connected? So in this case, we are saying it's 1 to 80. So here, what's the output predictions you want to make? So here it's like by default it's 1000. But in your particular case, depending on the problem you want to solve, then you use a different number. So in here, we are trying to predict 3 classes. Then we set it as 3. So, and one other thing I might want to talk about is this dropout here. So dropout here is more of a way to try to make your model learn effectively. So imagine you're still dealing with like some neural networks here to make some predictions where you have input and you have an output. So in most cases, let's say you have some fully connected neural networks that are connected to each other. So what happens they all try to participate in learning. So, and there's high likelihood to cause overfitting because every neuron is participating. So what they do there is just memorization. So you don't want the memorization to occur. So what you use is dropouts. So with dropouts, the key idea of dropouts is in some particular instance, you want to turn off learning of some neural network. So you want to force your neural network to learn using maybe this particular architecture at this particular point. So when you set your dropout, there is a chance that during some learning approach or some learning step, so a neural network is turned off. So your neural network and a neuron is turned off. So your neural network is forced to learn like using some constrained network. So in this part, something like this in this particular case. So overall, it kind of prevents overfitting and helps your model to generalize really well. So that's the idea behind dropout. So this percentage here is just telling you like 0.2. So it's just telling you 0.2. So what's telling you in maybe 1 out of 5, like with some uniform probability of 1 out of 5. So I want you to turn off 1 neuron from my network. So it helps to like boost the like generalization of your neural networks. So yes. So there's like key information here if you want to read more about it. So I won't run this because like previously we had some errors, but I'll just try maybe later on, I'll try to clarify the errors and maybe send you an updated notebook so that when you run it will be easier for you. So So in this particular point, what you want to do is to set your classifier. So you set the dropout, and here you set the layers that you have here. So just like we explained previously. So, and so when you have this classifier updated, so this is like the final layer of your pre-trained model, but you have changed it to fit the tags you want to predict in. So you could also look at like the input and output from like the predictions. So this is for the previous efficient net, but for this, I think I won't run this because we haven't updated anything for ResNet. So because of like the error we had. So, but it's just like the same idea overall. So when you have like this new model, so what you could do is just try to train your model. So what your model does, it try to adapt like the classification layer, that's the final layer, to your new tags. So it learns like based on like the new data to just make some good predictions. So everything stays the same entirely. So just to maybe recap, the most important thing when you are dealing with pre-trained model are just model that has been trained by someone else that works really well on particular task and you want to transfer it into a new task. So what you might need to be careful are two things. That's the input and the output of the model. So the output of your model, it's easy to decipher. So because the output of the model is based on like the labels of your new data. Let's say you are dealing with classification of diseases that are 5 in number, like definitely your output will have, let's say it will be predicting 5 values at the very end. So one other key thing you might need to note is, yes. So the other key thing is your input. So your input must align, the input that's your data input must align with the structure of your pre-trained model, of the input of your pre-trained model. So when you have those in place, so it's almost kind of guaranteed for your model to learn from that. So, and some of the issues that could arise is if, let's say you pick a model that doesn't relate or fit your tags effectively. Imagine in a particular case where you have a model that was trained, let's say you have an ImageNet model. So, okay, I think ImageNet works really well, but imagine you have a model that was being trained to identify maybe farm animals, and you want to use that model to identify maybe or to classify between textile materials. So it might work, but you might not have assurance. So in most cases, you could search for models that are closely related to your tags, and if they could work on your tags, so there is a high chance your model will work really well. So, but I think just to throw some questions. So assuming I am training my model and it doesn't work well, so what do you think is the problem, or what can I do to try to improve my model to learn? So you could just maybe answer on the chat, or maybe you could unmute your mic and maybe say something. So let's say you are using a pre-trained model and it's not training really well. So what can you do, or what might be the issues that you should look at? So, okay, I think before that, there's a question by Bala. So, how similar or different is transfer learning to fine-tuning? So I would say they are maybe arguably the same thing, just like term, like with the industry, you have various terms for the same things. So they are very much the same thing. So transfer learning is usually used in like the computer vision environment. So fine-tuning maybe it's like in the NLP kind of world where you have maybe language models and you want to align them to work on some particular tasks. So I think that's majorly what I was saying. Yeah. Thanks for the question. Yeah. So, okay. So just to recap briefly before we close, I think I kind of asked a question. Let's say your model doesn't work well. What do you think you could do to your model to to make it like run better. So there is an answer by Abubakar, fine-tuning the model or change the model. Yes. So one thing you could do is change the model. So because some model can be really large, and when you try to fine-tune them on a very small task, so it maybe doesn't give you the good results. So some case you might just want to use a smaller size model that has been used by someone and use that. Yes. So investigate other models for reducing. So investigate other methods for reducing overfitting. Yes. So maybe if you are facing overfitting, there is an answer by Aminu to reduce overfitting, maybe investigate other methods. So when you have overfitting, what you could do is like we talked about where you have, what's the name? Where you have dropout. So you could utilize dropout massively within your network. So it could help in reducing overfitting. So, and there is, I think, so the two are different. I can't honestly say maybe the two are different between transfer learning and fine-tuning. They are, let's say, mostly the same term. So, but used in maybe different domains. But mostly people mostly use transfer learning in computer vision, then fine-tuning in, what's the name, like NLP. But for me, I would say they are mostly the same thing. So, but where you have difference, let's say in NLP, you have pre-training. So then you have pre-training, then you have fine-tuning. So I would say pre-training is different from fine-tuning. But transfer learning and fine-tuning, I would say it's almost the same thing. Yeah. So there is a question from Sani Aji. Is there any clue of choosing the right pre-trained model for your task? I would say most times you would want to just, I won't 100%, I don't have an answer, but I would just say if like a task or a model has been used for any other task, like similar to yours, you could just use that. So, and in some cases, you just have to use it and see if it works well for you. But like with ImageNet, like ImageNet has like a lot of, have been used for like massively for almost different images. So in some cases, it will kind of work well for you, except maybe if the model is too large and your problem is too small. So that's maybe the case where it won't work. So there is a question by Farida. Is there difference between pre-training and fine-tuning? Yes, there is a difference between it. So I'm not really into NLP, but the way I understand it's like pre-training is like the initial first step of training, where you train like an empty model to learn to do, like you train the foundation model. That's like the very base model. So you use some kind of data set to train it on some, to do, so it just has like, you train it based on some particular data, but it's not able to streamline to one task. So you just like take all the data from the internet and give it to your model, and you have like some foundation model that is based on the entire data of the internet. Then when you want to fine tune, let's say you want to look at a very niche task. Let's say you want to look at maybe LLM for robotics. So you have trained this initial, you can look at it like the initial pre-training step. You train the LLM on a vast amount of internet text. Then you want to fine tune for robotics. Then you use some robotics data to fine tune on that LLM. So maybe that's what I can say about it. So yeah, so I think I will just thank so much for your time. But if you have any questions, feel free to ask, so that I think we have gone past time. And thanks so much for your attention. And so honestly, okay, there's a question by Bala. Transfer learning, inductive learning, transductive learning. I honestly don't know about this a lot, but I do know like in transfer learning, like there is like segments in transfer learning. So one of which is domain adaptation, where you take a model that is from a different domain to another domain entirely. So that's like a model that has been trained on a different data set. So let's say you want to predict maybe animals. Let's say like images in a different environment and another image in another environment. But I honestly don't know about the inductive transfer learning types. Yes. So I think I will just round up here. So please maybe just look at the notebooks, and there's an error with the notebook, but I'll just try to resolve it this night or tomorrow. But I think the major part is for this week and the next week, the notebook won't be your primary point of it's the capstone project, which I'll update by tomorrow, and we'll see how it goes, inshallah. So, so I think for that, I think this is where we'll round up. But if you have any questions, feel free to drop in the Telegram chat. But for this week and next week, you won't be doing these assignments. You'll be doing mostly capstone projects of individual projects, but to reflect on these assignments and everything we have learned in the previous classes. So, but feel free to ask any questions. And yeah, so if you want me to explain better, I will try to explain better, inshallah, because it feels like the class was a bit shaky for me. So, but I'm happy to talk more about it, inshallah. So thanks so much for your time. And it was kind of nice hearing from you. Thank you. Yeah, and remember to support Nigeria too. So bye, inshallah.
Thank you so much, sir.
Thank you so much. Take care.